video, we're going to look at the different factors that can affect the speed of sound. And hopefully we remember from the previous unit that there is only one factor that can affect the speed of sound. And so we're going to talk about how we can alter that one factor in a couple of different ways. So first, let's think of some terminology. So why do you see lightning before thunder? Well, it's because lightning is faster than the sound of thunder. So we see the flash of light before we hear the crash of thunder because of the difference in speed. One term is subsonic. These are objects that move slower than the speed of sound. That would be you. That would be most cars. There are very few vehicles that can go at or faster than the speed of sound. So subsonic is slower. Supersonic is faster. So subsonic and supersonic deal with speed of sound. Supersonic is faster than the speed of sound, so that would be light. That's why lightning, you can see lightning before you hear the thunder, is because light is supersonic. So two ways that we can change the speed of sound. One is we can change the temperature of the medium or the elasticity of the medium. And from last unit, we learned that the only way you can change the speed of any wave is by changing the medium. So we're going to see how temperature and elasticity affect that speed. So first is temperature. There's actually a special equation in order to determine the temperature dependence of the speed of sound. And that's that the speed is equal to 331 meters per second plus 0.6 times capital T. Here, capital T is temperature, specifically in degrees Celsius, not period. So it's the temperature dependence. Temperature. So let's use this equation. Find the velocity of a sound moving in air at room temperature. So the speed of sound is equal to 331 plus 0.6 times the temperature in degrees Celsius, which is 22. So we're going to multiply 0.6 by 22, which we get 13.2, and add that to 331, and so we get a speed of sound of 344.2 meters per second. Now this equation works only for speed of sound in air. It does not work for speed of sound in any other medium. If that were the case, if we were looking for speed of sound in water or a solid, we'd have to use a different equation with a different initial value for 0 and a different factor to then increase and decrease by. So again, this is only speed of sound in air. The other factor that affects the speed of sound is elasticity of the medium. So elasticity is just how much you can manipulate a certain material. So a very hard, solid object like a table has almost no elasticity, whereas something like silly putty has a lot of elasticity. You can manipulate it a whole lot. So speed of sound is faster in a denser medium than it is in a less dense medium, so that kind of plays into this elasticity. The more rigid the material is, the faster the speed, hence solids. Speed is faster in a solid, so it's faster in a more rigid material. It's slower in a more elastic. And the most elastic that we can think of here on Earth is probably going to be air. Air is very elastic. You can manipulate it very easily. You can bend it and shape it and do whatever you want. You put it in a certain container and it takes on the shape of that container. You can move through it very easily. I don't know about you, but I can't move through a table very easily. So definitely air is the most elastic that we have on Earth, hence it's slowest in that air. So more rigid makes it faster. More elastic or more fluid makes it slower. In this video, we're going to look at how we can apply the equations that we used for speed of waves and look specifically at problems that deal with those equations for sound. Of course, sound is a type of wave, and so any equation we use for waves will also be able to use for sound. So the two equations we used in the last unit are, of course, your DirectTV equation, which we used a lot last semester. And the DirectTV can also be put into the triangle, which is where DirectTV comes from, where you have D at the top, and then you have TV at the bottom. So DirectTV. The other one is the equation specific to waves, which is V equals lambda F, where V is your speed, lambda is your wavelength, which is just the length of one oscillation, and F is your frequency, which is how often those waves come through. Now we did have another version of this equation, which was V equals lambda over capital T, and that's because of the inverse relationship between frequency and period. So here, T is your period. That's the length of time for one oscillation. So this equation is really just DirectTV. V equals a type of D over a type of T. So our first example is going to use DirectTV. How do you know? It's depending on if it tells you to find wavelength, frequency, and period, or if it just gives you a distance and time. So this is sonar. Sonar is what boats use to figure out how deep the water is underneath them. We use this for mapping the ocean floor, as well as just figuring out military-wise if there are submarines or anything like that. So sonar is a method to use to determine the depths of the ocean. And how it works is that you have water, and you have the ocean bottom, and our boat sends out a signal. And the signal goes down to the ocean bottom and back up. So in this example, if this takes 2 seconds, and we have a speed in the water of 1450 meters per second, notice this is much faster than in air, then we're trying to figure out how deep the ocean is in this particular location. So this one is a DirectTV problem. So V equals D over T. Now, since it's 2 seconds down and back, then one direction is going to be 1 second. So to find our time, we're just going to divide by 2, which gives us 1 second. So V is 1450. We're looking for D, and T is 1 second. So we're going to multiply 1 over. We get a D of 1,450 meters. So actually not very deep. Our second example is now going to use our other equation because it specifically says in it frequency, and we're looking for wavelength. So wavelength, frequency means we have to use the other equation, V equals lambda F. So we're given the frequency of 256. So we're going to plug that in for F, and we're given the speed of 343. Notice, yes, definitely in air, sound is much slower than in water. So then we're solving for lambda. So again, it's just going to be a simple division problem. So 343 divided by 256 gives us a wavelength of 1.3398. So one thing to think about is sound waves, a lot of them can have really long wavelengths. So middle C, if you play piano, middle C is the very middle of the piano, hence middle C. And so that has a wavelength of 1.34 meters. This is why the string inside the piano has to be so long, is because it has to be able to vibrate at a frequency to create a wavelength of such a long wave. 1.34 is about 1 1/3 meter sticks. So middle C string is usually about that long.